case. Now moving ahead, we'll try to understand the second case, in which we are having a fixed beam with a uniformly distributed load. Now by this time we know how to understand this particular type of the problem. So moving ahead, this is a combined effect of the fixity and the simply supported beam. So this value of VA and VB are nothing but these are the reactions due to the simply supported beam, whereas the couples at A and B are nothing but due to the fixity at A and B. So let us understand the things in a separate way. So in this figure 3 you can see I have shown the simply supported beam with the reactions WL by 2 and WL by 2 at A and B. Going ahead, I know what is to be done with this particular simply supported beam. I have to draw the free bending moment diagram, and that comes out to be equal to WL square by 8. Moving ahead, I'll simply consider the effect of fixity now. So here only because of that fixity there will be the couples acting in this particular direction at point A and B. So this particular figure 5 gives you the simply effect of the fixity at point A and B, and when I will be combining this fixity effect along with the simply supported beam effect, I will be ultimately having this, which is diagrammatically shown in this particular figure number 1. So this is how we have to find out the fixed moment diagram at this particular point. So here you can see MA and ME, MB. So this is MA and MB, and I am very much interested in finding out this value of WL square by 12 by the further analysis. At this moment I have directly substituted here, but for getting this particular value I have to do certain mathematical modeling from the knowledge which we have got from the earlier discussion in this video as well as in the earlier video. So moving ahead, we can see again in this particular case this beam is a symmetrical beam. So I know what is to be done with this, or what we have to understand out of this, that whatever reactions we will be having for a simply supported beam, they will be same, that is VA is equal to VB, that is equal to WL by 2 and WL by 2. And from the first principle we came to a conclusion A is equal to A dash. A is nothing but it is the area of free bending moment diagram, and A dash is the area of the fixed moment diagram. So having this particular understanding and simplifying here, so left hand side is A and right hand side is A dash. So here you can see I have found out the area of a free bending moment diagram. This being a parabola, so I know what is the area under parabola, that is 2 by 3 A of B. 2 by 3 of A means what? Span, and B means what? Is the vertical height, that came out to be equal to WL square by 8. This is nothing but it is the maximum bending moment of a simply supported beam. So here I have substituted the value for A and A dash, that came out to be here. So again from this we can see that if I cancel out this L and L, what ultimately I will be having is MA is equal to WL square by 12. Is it okay? Now I have shown it here equal to MB because this is a symmetrical figure. So MA should be equal to MB, and that is why I have shown this figure as a rectangular figure, because I knew MA will be equal to MB due to the symmetry of this particular figure. Now going beyond that, I know that I have to find out the slopes and deflection. For that particular reason I have to work out certain things. I know what is the basic mathematical equation we are going to use for finding out the slopes and deflection, that is EI d2y by dx square is equal to bending moment, and here bending moment is the resultant bending moment at that particular center, which will be found out in the next slide. So here once again I have tried to show the same diagram which we have studied earlier in the earlier slide. So simply supported beam, its free bending moment diagram and its fixed moment diagram due to the fixity, and I have superimposed both the diagrams one above the other. So here you can understand what I was talking about, a resultant bending moment at the center. So here, as we have seen in the earlier case, this is a line which is neutral, because below this there are negative bending moments and above this there are positive bending moments. So ultimately at this particular point the resultant bending moment will be bending moment at the center due to simply supported beam minus bending moment due to the fixed moment. Is it okay? So moving ahead, earlier only we have found out the resultant bending moment for this particular case. So this being a simply supported beam, I have considered a section XX at a distance of x from point A. Now in that particular case, we know that in the earlier case, this value, how we have worked out, this is for the sake of this particular first simply supported beam, means these two terms in this M are related to this particular thing about point XX at a distance of x. So if I take a moment about point x, so WL by 2 moving in the clockwise sense, a positive, so WL by 2 into perpendicular distance x, and as far as this UDL is concerned, it is acting in the downward direction, means what, it is going to form an anti-clockwise moment, so that is why it is minus. So the WL by 2 into x minus WX square by 2, WX square by 2 is nothing but it is the moment due to this particular UDL imposed up to a distance of x minus WL square by 12. Now this WL square by 12 is already been found out in the earlier figure. Here you can see here. So at this moment, at this particular XX section, if I take a moment on the left hand side, so on the left hand side there is only MA, and it is in the anti-clockwise sense, it is trying to hog that particular beam, so it is minus MA, and we have already concluded what is the value of MA, that is equal to WL square by 12. So this is what we have shown in this particular figure also. So here WL square by 12. So calling this as equation number 2. Now from the superimposed bending moment diagram in this particular figure, you can find out the point of contraflexure as we have found out in the earlier case also. Now for that particular case, I have told you that at this particular point here, the bending moment is to be equal to 0. That means whatever bending moment equation we have found out, if I equate with 0, I will be having the simplification of that particular equation. So here x square minus lx plus l square by 6 is equal to 0. We are getting with a quadratic equation. Solving this quadratic equation, I will be getting a value of x. So here you can see I have got two values of x. X is equal to L by 2 and x is equal to plus 1 by 2 under root 3, and another value will be what? X is equal to L by 2 minus L by divided by 2 under root of 3. So these are the two values of point of contraflexure. First value is related to this and second value is related to this. So this is how we have to work out the values for the point of contraflexure also. Now in this case, if you try to understand what are the procedures to be adopted for finding out that particular thing, that is what the fixed moment at point A, and how this particular point of contraflexure is to be found out. So these two things we can very well understand up to the knowledge which we have gathered here. Now let us move ahead to find out the slopes and deflection for that particular beam. Here you can see once again I have drawn the same figures. So here I know that for establishing the relationship between the slopes and deflection, I need the basic mathematical equation giving this relationship between bending moment EI and the deflection and the slopes. EI is equal to d2y by dx square is equal to m, and m already we have found out in the earlier slide, so I have substituted that particular value. On integrating, we are getting EI dy by dx is equal to WL x square by 4 minus WX cube by 6 minus WL square L square x by 12 plus C1. So as usual, to find out the value of C1, we will be having the boundary condition from this basic figure. So at x is equal to 0, slope is 0, therefore C1 is equal to 0. Put it in this particular equation, you will be having a new fresh equation for the slope, that is EI dy by dx is equal to Wx square by 4 minus Wx cube by 6 minus WL square by 12x. So this is what is the new equation of a slope. Again integrating it, we are getting this simplification. So after simplifying, we are coming across another value of constant for the integration C2 that can be again found out from the basic discussion. So x is equal to 0, so the deflection is equal to 0, therefore C2 is equal to 0. By putting this value of x is equal to 0 and y is equal to 0 in this equation, we will be getting C2 is equal to 0. So back substituting the value of C2 in this equation, we have a fresh new equation for the deflection, calling those two equations, equation number 1 for slope and equation number 2 for the deflection. So this is how we are going to find out the slopes and the deflection for that particular thing. Once again, here you can understand, for any value of x means I can find out the slope and deflection at any value of x from 0 to L. So consider that particular value of x, put it in the equation 1 and equation 2, you will be definitely getting the values of slopes and deflection. Now moving back to the basic, here we know that this being a beam which is symmetrical and ultimately at the center there will be the maximum deflection. So for finding out the maximum deflection, I know x is equal to L by 2. Substituting s is equal to L by 2 in this particular equation of deflection, I will be getting a value of deflection at the center, which I have called it as yc is equal to minus w L raised to 4 384 by EI. Once again, we can compare the deflection of a beam which is simply supported imposed with a UDL throughout the span, and this particular fixed beam imposed with the UDL throughout the span. So here we have a conclusion. So the deflection of a fixed beam is always equal to 1/5 of central deflection of a simply supported beam with a UDL. So this is what is a basic conclusion which we can draw out of the discussion of this particular case number 2. So I hope you all are getting what is going on in this particular analysis of the